Alright guys, so today I'll be talking about the Franck-Condon principle. So the basic criteria about Franck-Condon principle is in the vibrational energy level, how the electronic transitions are going on, how the electronic transitions are operate. This Franck-Condon principle is actually a part of electronic transition when you go into the deeper down of how the energy levels are actually working, how the electrons are actually working in the in the vivid energy levels manner. So that is when we need the Franck-Condon principle to understand that part. Okay. So before we understand about Franck-Condon principle, before we start talking about Franck-Condon principle, the first thing that we need to know is how the vibrational energies are working first. Okay. So I guess guys, you are pretty much familiar what happens when two atoms comes closer to each other in order to make a bond, make a chemical bond. What I mean to say is, okay. So let's say, okay. By the way, whenever I'd be writing something, I'd be looking at that side of my thing. There is another screen in there. That is where I'll be. Now have a look in here, guys. Let's say there is an atom A and there is another atom B. Okay, when these two atoms are coming closer to each other, you know that what is going to happen? The nucleus of A is going to attract the electrons of B. The electrons, those are there in B. So nucleus of A, I'm going to write the attraction forces here. So the nucleus of A and electrons of B are going to attract each other. This is the attractive force is going to work, right? Then similarly, the nucleus of B and electrons of nucleus of B and the electrons of A, they are also going to attract each other, right? So these are the attractive forces, those are going to work in here. Now similarly, there are some repulsive forces going to work in there as well. So what are the repulsive forces working in there, guys? So if you have a look in here, the repulsive forces would be the nucleus of A and the nucleus of B, and the electron of A and the electron of B. So the electrons of A and electrons of B, these electrons, all of them are negatively charged, so they would be repelling each other, and the nucleus would be repelling each other as well. Similar charges. So as a result, when we draw an energy diagram, energy level diagram for them, what we get to see is, let's say this is my potential energy. So what we get to see over here is, guys, more they come closer to each other, the energy keeps on decreasing. Now why is the energy decreasing over here? Because guys, as they're coming closer to each other in distance, like, okay, this is the nucleus of A atom, and let's say this is the nucleus of B atom. So I'm just bringing them closer to each other. So what would happen then? So at first, the attractive forces will be predominant. The attractive forces will be predominant. As a result, what would happen is their energies would keep on going down. Means they are gonna be coming more and more closer towards stability. You know that whenever chemical bonds are being formed, they become stable in their life, right? So because of that, what is gonna happen is their energies are gonna go down, right? Now it would go down till a particular level or till a particular distance. I forgot to tell you, in my x-axis, in my y-axis, I have the potential energy. In my x-axis, what do I have? I have the radius. What is the radius? I mean internuclear distance, you can say. So R is nothing but the internuclear distance. Internuclear distance. Okay, so R is the internuclear distance. Means the distance between two atoms nucleus. Means when we are coming, letting them come closer to each other, so there is an attractive force working. The attractive force is nothing but these two things. The attractive forces are working. As a result, what's going to happen, guys? It is going to come closer and closer to stability. Attractive forces are going to take them to stability. But after a particular point, let's say this particular point onwards, what would happen now? Now the repulsive forces would start their work. As a result, what would happen is, guys, in the short range, as the repulsive forces are working, so now they would start becoming destabilized. And more you come closer to each other, the destabilization increases. Okay, so that's why they say that the distance at which the potential energy is minimum, the distance at which the potential energy is minimum, this distance is actually the bond length between A and B. So guys, what is the bond length between A and B? The distance which is at which the potential energy is minimum. Potential energy minimum means that is the most stable situation for it. This entire diagram that I have drawn over here, this is in the vibration energy level. We call it the Morse diagram. We call it the Morse diagram in the vibration energy level. So what do I mean by this vibration energy level? See, actually what happens is, I have drawn this entire diagram considering the both the atoms are there in their ground state. They are in their ground state. Ground state means they have 0 point energy. 0 point energy means the stable energy. Okay, whatever the energy they are supposed to have, they have that much. All right. So we are considering this is where the potential energy supposed to be for the system when they are making a bond. That means, let's say I'm talking about HCl. So let's say HCl's bond length has been found to be as 0.35 angstrom. That means at 0.35 angstrom, it is hitting the lowest of the potential energy, right? But guys, that is not actually true. This is not actually true. The truth is, whenever a molecule is at its minimum energy level, then also it has some vibrational energy, translational energy, and rotational energy possessing within itself. So that means the energy of the electron, the system is never really at the bottom of the well. It is somewhere here in this level, and in that level, the atom is not really static. Even in the minimum energy level, because of the rotational, vibrational, and translational motion, they are actually moving, guys, even in their lowest energy level. That means, I'm going to show you only one of them. I'm going to show you the vibrational energy level right now, because that is our target. So guys, they are vibrating like this, from this to this. If I move on to a little bit higher energy level, the atom is vibrating like this. The bonds are vibrating like this. In a little higher energy level, it is vibrating like this. So like a normal simple harmonic oscillation, guys, it is vibrating like this. It is vibrating. The molecule is vibrating. The bonds are vibrating. I'm going to show you all these vibrational modes, guys. There are 3 types of modes that we can see. For, let's say, I'm going to show you for water. I'm going to show you which all modes are they going to make right now. Okay. So I'm going to share my screen with you in order to show you how the molecules are vibrating even in their lowest energy level. Okay. So if I just share my screen here, you can clearly see. You can clearly see I'm showing you the water molecule right now, isn't it? So what I have done is I have calculated the energy of the water molecule in the lowest possible energy. That means, guys, I'm talking about the minimum of the potential energy well. After I have done that, now I have seen that there are 3 types of vibration that this molecule is contained. Now, what are the vibrations? Let me show you here. So vibrations are of 2 types, stretching and bending. I'm going to show you all of them. So let's start with the first kind of vibration that it is making even in their ground state. As you can see over here, this is called symmetric bending. So we thought that the molecules might be constant in energy, but that is not really true, guys. Even at its lowest energy level, it is bending like this. Alright, the molecules are bending like this. This is called symmetrical bending. What else kind of vibration would water molecules show? See, the second one is symmetric stretching. The molecules are stretching, right? You can see the vibration right now. And the third kind of thing that it has is asymmetric stretching. As you can see, it is not really symmetrical, right? It's asymmetric. So these are the 3 types of vibration that a molecule might possess. Okay. So now I'll be taking you back here. Now over here, what actually happens is, so in every energy level, it has a particular vibration. Okay. So let's consider this vibrational energy level is V0. The next vibration energy level is V1, then V2, then V3, V4. So all these things are vibrational energy level. So the molecule is actually vibrating in this level when it is in the lowest energy. So the vibrational is happening in this level. But guys, if I keep on giving him some energies, then what would happen? Achha, what kind of energy am I gonna give? to change the molecule's position from here to here, if I have to increase the vibrational energy of a molecule, then what am I gonna do? What kind of energies are we gonna do? We would be giving IR, infrared kind of energy. So when we give infrared energy to a molecule, what happens, guys, over there? The vibrational transitions happens. Means the electrons of the molecule from one vibrational state to another vibrational state, they make a jump. From here to here, they make a jump, or here to here, they make a jump. All right. So now they make a jump in IR whenever we are giving the energy in the IR level. Okay. By the way, I guess we all know that with respect to energies, infrared has the lowest energy. After that, we have the visible energies. Then we have the UV energy. So from left to right, if I go, the energy is actually increasing, isn't it? Okay. Now, what would happen instead of IR if I give them UV level of energies? Okay, guys, I haven't really started teaching you about the Franck-Condon principle so far. So I'm just telling you the rest of the things so far. So what would happen if I, instead of IR frequency, if I start giving it a UV levels frequency, then what would happen? Then what actually happens is, guys, the transition won't be occurring in the vibrational level anymore. It would be occurring in the entire energy level. Let's write it down. So IR energy or frequency, it is responsible for transition in vibrational level. So IR is responsible for transition in vibrational level, whereas UV energy, it is responsible for transition in the entire energy level. The entire energy level. Means, what I mean to say is, let's say I'm going to draw two energy levels right now. Okay. Let's say with respect to potential energy, this is one energy level, the potential well with respect to one energy level, and this is the potential well with respect to another energy level. Okay. Okay. This diagram that I have drawn, it is a little wrong actually. Okay. I forgot to draw the vibrational energies. So yes, so the diagram I have drawn, it is a little wrong. You know what? First of all, if you haven't forgotten, guys, if you haven't forgotten, then from the 0 point, it was a 0 point. From the 0 point, let's keep it here, to this point. What was this distance, guys? This was the bond length, right? We can call it the internuclear distance, isn't it? Internuclear distance, right? So when I increase the energy, okay, this is my ground state. Well, this is V0, V1, V2, V3, V4, all the vibrational mode. Here it is V0 prime, V1 prime, V2 prime, V3 prime. What are these? These are the energy, these are the vibrational mode of energies in the first excited state, in the higher energy level. So if this corresponds to some energy like 20 kilojoules, then this potential well corresponds to an energy like 100 kilojoules, something like that. All right. So it's in the higher energy level. So what actually happens is, they are saying the higher energy level, if you go, the potential, the internuclear distance. What is the internuclear distance? This distance. This distance actually increases. Means the potential well is supposed to look like a little bit in the sideways, like this, a little more to the right hand side, because the internuclear distance are supposed to be increasing. So let's just visualize this, why it is supposed to happen. Okay, what is the logical reason behind this? So if you have a look again, All right. So I'm going to again show you what would happen. So let's say I'm starting the animation again for asymmetrical stretching right now. Okay. Okay. You can see it, I guess. Now what would happen if I increase the energy? So right now, if I just stop the animation right here, and if I try to look into, just one second. If I just try to look into the bond length right now. Yes. Okay. Oh, just one second. So actually, I just close the diagram. Okay, it would just take some time for me to reset it and reopen it. So what I was actually telling you is till the time. So when actually what happens is when you're increasing the energy, what actually happens is the internuclear distance is gonna increase. Now, why would that happen? So the logic behind this is yes. Yes, I found it. View question CH4. Would this work? No, it won't. Just one second, guys. Now if I can just show you this, it would be much more easier for you to actually relate this thing. There you go. I found it. So water. Yes. Okay. So now I'm going to share my screen again with you. So I guess again you can see the water molecule that I was talking about at that time. So what would actually happen is if I increase the energy of the system, then what would happen? So if I can show you this here. So when we are increasing the energy of a system, what actually happens is the bond length, like you can see I'm increasing the energy, then what's happening? The bond length is increasing. Means the internuclear distance is increasing. Now think about it. If I just keep on increasing the energy, the bond length would keep on increasing and keep on increasing, and there will be a time when the bond would break. That is what happens when you increase the energy, isn't it? The bonds, they break in there, right? So guys, this is the exact thing what is happening in here as well. So by increasing the energy, what is supposed to happen? The internuclear distance is supposed to increase in there, right? So let's go back to the blackboard now. So yes, so like I was showing, so here the internuclear distance is supposed to increase by a little bit. That part is clear. Now, as it is supposed to increase by a little bit, so now my vibrational energy diagram is supposed to shift a little bit to the right hand side. And now, if I give it a UV level energy, then what would happen? Then the electron which is present in the lowest vibrational mode, it is supposed to take a jump straight to the, let's say, from here, the electrons is here. It's supposed to take a jump straight to the energy level. So you know that what actually happens is the energies, the electrons can only take a jump which is perpendicular. It cannot take a jump like this, here to here jump. This is not possible. It have to take a jump which is perpendicular always. So guys, from where to where the jump is happening? So the jump is happening from zero, from the in the ground state, level 0, to in the excited state, level 1. Okay, this is the jump which is happening. So if I have to draw the intensity peaks. So where am I supposed to see the maximum intensity? So let's say 0 to 0 transition, 0 to 1 transition, 0 to 2 transition, 0 to 3 transition, and all those things. So which transition is actually happening, guys? 0 to 1 transition. So there I'm supposed to see a peak like this, and all the other transitions probability or possibility should be low in way. Now this is where actually the actually the Franck-Condon principle comes into the point. So they are saying no, the internuclear distance is not really changing. Okay, so what is the logic behind this? They are saying that this diagram is not correct. The correct diagram is when the internucleus is energy is not at all changing. It is exactly the same like the ground state. They're saying that I'm gonna come to the statement of the Franck-Condon principle. They're saying that the electronic transition is happening not from 0 to 1, it is actually happening from 0 to 0. So that means this intensity peak is wrong. Actual intensity peak is 0 to 0 transition is highest intensity and the other intensity peaks are less. So is the thing clear to us? Now, why is this happening? Why is Franck-Condon principle saying that the energy of the internuclear distance is not supposed to change? So let's write it down first. So according to Franck-Condon principle, the internuclear distance won't change during electronic transition. Now why is that? Why won't it change? Because the electronic transition are very quick and random. They are so quick that the internuclear distance won't get a chance to increase. When it would think about increasing the internuclear distance, by then the electronic transition would happen and it would come back as well. So not only the electronic transition would happen, it would also come back from there. As a result, guys, it happens so quickly that the internuclear distance couldn't get the chance to change. Now, this is also a use of Born-Oppenheimer approximation. So why is it happening? Why the internuclear distance is taking more time to change and the electronic transition is taking lesser time? I'm saying that electronic transition would happen and come back by when the internuclear distance would change. So why is that? What is the logic behind this? According to the Born-Oppenheimer approximation, we know that the nucleus are very, very heavy than the electrons. As a result, they would take more time to change the internuclear distance than the electronic transitions are going to happen. So this is the classical example. This is a classical proof of Born-Oppenheimer approximation. So guys, that is why Franck-Condon principle is saying no, the internuclear distance won't change. It would be a transition from 0 to 0 and the intensity of the peak from 0 to 0 would be the highest. So I guess you have understood what is the Born-Oppenheimer approximation is, and I guess I could make you understand about this entire topic. Okay, if you have understood this, then definitely like this video, and if you couldn't understand this, so just leave a comment in the comment section. All right, so that would be it, guys. Bye everyone.